Okay, hey, we're going to talk very quickly about how it is that we graph a linear inequality. So first things first, let's talk about some notation here. An inequality here, so if we're graphing a linear inequality, just to carry over from before when you're graphing on number lines, where if it wasn't equal to it was an open circle, and if it was equivalent to it was a closed circle, so just taking some knowledge of when you had the number line and which way you would shade. So if on the x-axis it was left or right. Well, now we're going to talk about setting it up so that we have a linear equation. And linear equations are y equals mx plus b. So now we're going to be talking about some y value being greater or y value being less than. So notation again. So carrying on here. So if it was greater than or strictly less than, then it's going to be an open circle at my marker point, and it's going to be a dashed line. So that's the new terminology, that it's going to be a dashed line. If it is greater than or equal to or less than or equal to, it's going to remain that closed circle, except now we're also going to include that it's going to remain the same, so it's like you've always graphed. So the new other things here we're going to talk about is if y is greater than or y is greater than or equal to, the shading is still going to be the same. We're going to shade up because as the y-axis goes up, y values get greater. So that's why the y is greater than, and for the vice versa, for the y less than or equal to, we're going to shade down. So let's take a look at an example. So an example I have here is y is strictly less than 2/3 x minus 1. So we do the same exact principles as we did before with y equals mx plus b. So this here is going to be, okay, the -1 is going to be my y-intercept. So I go to -1, except now I have to think about what type of marking am I going to put there. Am I going to put an open or am I going to put a close? Well, if we take a quick look at the notation says here, because it's not equal to, that value really doesn't exist, but for this boundary line that I'm creating, that's where the boundary line goes through. So I put an open circle. So open circle there. I then utilize my slope like normal. So my boundary line, to keep it going, I go up 1, 2, over 1, 2, 3. So I put an open circle. Now, since I have open circles, what I'm going to do is I'm going to connect those two open circles with a dashed line, because this boundary line means that these values really can't exist on this actual line, but they're going to exist elsewhere. So here we go. I'm going to connect it with a dashed line. So there's my dashed line. So I have now got my dashed line. Now, what an inequality represents is it doesn't actually have to be equal to that actual picture. What it could be is it could be just any coordinate pair that's going to make a true statement. So up here, if I take a look at this, it says y values are going to be less than. So if I go anywhere on this line, I want y values that are going to be less than that actual coordinate. And we're talking about strictly straight down in this case. So if I go to this point, okay, I want to have all the same x coordinates, but I want them to be less than that. So I'm going on here, less than this. So right here, if I take a look at this, this is when y is -3. So for it to be less than, they have to be down here. I can pick any other y coordinate below. The x would be the same, but any other y coordinate below. So what we do is that I can't literally list all of these possibilities and all these coordinates. So what I do is I call shade in the region, which the shaded region then goes to show that that shaded region goes forever and ever and ever, expanding over all coordinate pairs. So what we do here is we say that we shade this. And the shaded region represents all of my possible solutions. So there's my shaded region. So my final graph just simply looks like I have a boundary line that no value can exist on this line, but all the values below it, if I picked any coordinate pair, would make this a true statement. And just to demonstrate that, let's pick the number 1, 2, 3, 4. We're just going to pick something very simple as I'm going to pick 3. Sorry, let me pick 3. So the coordinate pair 3, 0. If I plug the coordinate pair 3, 0 into here, it will make a true statement. So here we go. I'm checking the coordinate pair 3, 0. And the way that I check it, I just simply plug it in. Well, this is y, so plugging it into here, I say 0 is going to be less than 2/3 of 3. And then subtract 1. Well, let's just check if this makes a true statement. So, is 0 less than 2/3 of 3 is 2 minus 1. Is 0 less than 1? So 2 minus 1 is 1. Well, is this a true statement? Well, of course it is. 0 is less than 1. So because this makes a true statement, that just goes to show you that the fact is that it's not worried about if it's equal to anymore like it was an equation. We're just worried about what coordinate pairs will make true statements, and it just so happens to be that any y value that's below any point on this y-axis will always be true, so I can shade in all area. Okay, so I hope that helps for graphing linear inequalities.